For your consideration, a SmartIce vaccine cooler. It is a low-cost, open-source, temperature-controlled cooler for transporting vaccines to remote communities around the world. In 2020, the COVID-19 epidemic and the virus that causes it, SARS-CoV-2, quickly swept around the globe. While international efforts to develop an effective vaccine are underway, the distribution of that vaccine is a problem all of its own. The initial COVID-19 vaccine will require refrigeration. Inoculations will need to be kept chilled between 2 and 8 degrees Celsius, or they will essentially spoil. Equally destructive is freezing them with uncontrolled chilling. In the developed world, the scale of this distribution problem is difficult to comprehend. To try to put things into perspective, the International Renewable Energy Agency reported in 2019 that roughly 840 million people live without electricity. 840 million is fully 11% of all people in the world. That is to say that 11% of people will have a difficult time receiving the COVID-19 vaccine simply because we can't keep it from spoiling. There is a need in the world for low-cost, mobile, off-grid, temperature-regulated refrigeration. Current off-grid refrigeration used for vaccine transport falls into 2 categories, active and passive. Active systems are temperature-controlled, but they require constant sources of electrical power. This adds weight, cost, and complexity. Passive systems get around the issues of cost and complexity by using ice of one form or another. Dry ice provides excellent cooling capacity, but it comes at a high risk of freezing the cargo. Water ice is generally considered to be the most safe, but it is extremely heavy for the cooling power that it provides. This project demonstrates a hybrid approach to temperature-regulated cooling. I'm calling it the SmartIce Approach. This proposed system combines the compact cooling capacity of dry ice with the temperature control precision of a low-power electronic microcontrol system. The simple-to-build cooler solves the problem of freezing by placing a block of dry ice in a separate chamber below the cargo compartment. A low-cost, brushless PC fan then circulates small doses of super-chilled air up through the cargo compartment as needed. This fan is controlled by a robust microcontroller running a temperature control loop. This hybrid approach allows for a low-cost system which can be mobile like an ice chest and have digital temperature regulation like a plug-in refrigerator. Tests run with a full-scale prototype showed that 5 degrees Celsius could be maintained for up to a week with a single charge of dry ice and only power from a single rechargeable battery. The cooler itself is made of construction-grade urethane or polystyrene foam sheets, sealed with caulk and wrapped in foil insulation as a radiant barrier. After nearly a year of experimentation, I built a working prototype that satisfies the following requirements: 5 gallons or 19 liters of cargo storage space, cooling capacity enough for 7 days at 5 degrees Celsius in an ambient temperature of 20 to 30 C, temperature precision of plus or minus 1/2 degree Celsius. The finished system costs around $200 in materials to build and is light enough to be moved over rough ground by one person using a hand truck. This project is designed to be built by engineering students and motivated groups of aid workers around the world. The required supplies, including dry ice, are generally available in most of the world's cities, even in the poorest countries. It is my hope that universities will choose to replicate this research and then find avenues to apply it in the real world, and hopefully save some lives in the process. Thank you. Please see the links below for more information and for downloadable files related to this project.